Okay, good evening, class. So let's start tonight's tutorial. So we'll carry on with hypothesis testing. So just to recall this hypothesis testing, so there are actually 4 steps. So it's a very structured way of solving this kind of problem. So 4 steps. So the first step is we'll write down the H0 and the H1. Okay, yeah, write down the H0 and the H1. H0 is called what? Null hypothesis, and then H1 is called alternative hypothesis. Okay, so this H0, no matter what, we just don't care. We always just go and put the equal sign. Okay, and then this H1, oh, this one you need to care a lot. You need to go and choose correctly. So should we choose less than, more than, or not equal? Okay. So we just remember that H1 is actually the statement that we want to test. Okay, the thing that we want to test, we'll put it as H1. All right. So that's H0 and the H1. So we just write it down. And then the second step there, we'll go and calculate this test statistic. Now, different tests has different test statistics. All right. And then we'll go and draw rejection region. And then after doing this, then we'll see this test statistic here in step 2, does it fall in the rejection region? If it falls in the rejection region, that means we'll reject H0. Okay? If it falls in the rejection region, means reject H0. And if it doesn't fall in the rejection region, that means cannot reject H0. And we will go and reject H1. All right? And when we reject one, meaning that we'll accept the other one. Yeah. So then we can go and draw a conclusion, accept what, reject what. Okay. And then not just like that, we want to write something about H1. All right. Whether you are write in words about this H1. So usually the question will ask something, right? So here we need to answer to the question. Okay, right. Let's go to the next page. Yeah. Okay. Let's go to the next page. Okay, so this is the tree that I showed you last week, right? So this one, you can see that hypothesis testing, we actually test 2 things, right? You test mu or you test sigma square, right? And then let's look at each one. Let's look at sigma square first. So when you are testing the population variance, now you see here 2 points, right? The first point is actually the prerequisite, right? That's the prerequisite here. We want X to be normal. And the second point here is actually the test statistic. So that's why you see here, when we are testing population variance, the test statistic is always the chi-square. All right, so this is the chi-square, n-1 s square over sigma naught square. And it will be of degree n-1. Okay. And then coming to testing of population mean, you know there are 2 cases, right? So it depends on whether sigma is known or sigma is unknown, right? And then you see here, each of them also got 2 points here, right? The first point, well, actually it's the same, is the prerequisite, is the requirement. So you want X bar to be normal, okay? And then the second point is the test statistic. So you see, when you're testing mu, when sigma is known, the test statistic is Z. And when sigma is unknown, the test statistic is T. Okay, right? Yeah. So this slide is about the prerequisite and also the test statistic. Okay, right. Now we talk more about the prerequisite. Now this one here, now you see you want X to be normal, right? So this one is very easy. You want X to be normal. One way is the question tells us, right? Then another way is, well, the question doesn't tell us. Then what we do is we just go and assume. Just go and assume that X is normal. All right, so this one is very simple. If you don't have it, you just go and assume. All right, so there's no theory behind. But this one here, this one not so simple lah. And see here, the prerequisite is you want X bar to be normal, right? Or approximately normal. Now, how do we make sure that we have this? Well, then we actually have you see, we have this slide here, which is inside our lecture notes. You see this is a page number. So how to ensure that X bar is approximately normal? So it depends on your sample size. All right. Now, if your sample size is below 30, now here you cannot use central limit theorem. All right. So what we do here is you assume X is normal, then X bar will also be normal. And another case is if the sample size is greater or equal to 30. So in this case, straight away we can use central limit theorem. That will give you X bar approximately normal. Okay, now, all right, so just like that. Okay, let's go back. Go back here. Right, so we've done this one already. Now you go to another page. So this page is about the rejection region, now also known as critical region. So our rejection region actually got upper tail, lower tail, two tail. All right, so that's why you see all these upper tail, lower tail, two tail, right? And they all depends on our H1, whether it's more than, less than, or not equal. Okay, now you see here, your H1. So all of y'all can hear me, right? Okay, so here, and you can see the H1 is more than. All right, so if your H1 is more than, that means you are getting upper tail test. So you can see your rejection region, they are the upper tail. Okay, and the area of the upper tail, you can see that the area is alpha, right? And you see the shaded region, the rejection region, the area is alpha. Now this alpha is called what? Level of significance. Usually it's given in the question, right? Now lower tail is like that. This is called lower tail. So when do you get this? When your H1 is less than. All right. And finally, we got two tail. Two tail is H1 is what? Not equal. Okay, so we see here there are two tails, right? Then what about the area there? Now, when you have two tails, each of the area will be alpha over 2. So that when you add up, you will still get alpha. Is it okay? All right, so just like that. So that's about hypothesis testing. So we are ready to go to our next question, right? So before we go to our next question, once again, this is our most favorite slide. All right. Okay. So when we read the question, we need to know what is X. We need to identify the random variable X. All right. So there are two hints to help us. So this is the first hint, mean of something, variance of something. So your X is that thing. Okay. So you just go and look for, mean of what, variance of what, standard deviation of what. So they are mentioned in the question, right? Okay, another thing you can look out for is when they say something has, well, certain probability distribution. Well, maybe it's normal, okay? Then your X is also likely to be that thing, right? And when you put down our X, we got to write it in a singular form, all right, not plural, meaning that, for example, X is what now? X is the height of a student. Okay. All right. Okay, so having done all these things, so now we can go and look at our question. Okay, so everybody is seeing the question here, right? Okay, let's go and see this question. Okay, so we'll read the question, and as we are reading, we will identify the big X. Okay, we'll try to identify the big X, and also those numbers. They give us some numbers, right? We also want to identify what are these numbers. Okay. All right. So we have a new brand of canned mixed nuts, plans to enter the Singapore market. Right. So the label says that 25% of the contents are cashews. Okay, so this is what the label says. The label says that 25% of the contents are cashews. So suspecting that this might be an overstatement, an inspector takes a random sample of 31 cans. All right. And he measures the percentage weight of cashews in each can. All right. Now let's analyze this. First of all, this inspector takes a random sample of 31 cans, right? 31 cans. So what is this 31? Yeah, anyone? You just unmute and tell me.
Small n.
Yeah, that's right. So this one is actually our sample size n. All right. So n is 31. And then this inspector, what does it measure? He measures, what does it measure? So we notice that he measures the percentage weight of cashews in each can. All right. Now he measured this one in each can. Now what is this percentage weight of cashew? So it's actually explained here. So it's a weight of cashew divided by weight of all nuts and then times 100. So that's the meaning. Okay, right. And then we carry on reading. Now the mean and standard deviation. Can you see this word mean? You also see this word standard deviation, right? Okay, so be prepared. Mean of what? Standard deviation of what? Now mean and standard deviation of these measurements. Oh, mean and standard deviation of these measurements. All right. Whatever that measurements are. Well, the mean is found to be like that, and the standard deviation is found to be like this. Okay. Now let's see. Now mean and standard deviation of. Now you know from our hint, we know that this one is mean and standard deviation of x. All right. So this is likely to be our big X, right? And then this big X is these measurements. So what are these measurements? What kind of measurements? Yeah, the diameter of the nuts. What do they measure? Do they measure the
weight of the cashew?
Cashew?
The percentage weight of cashews.
Yes, it's the percentage weight of cashew. So you notice that the inspector measures the percentage weight of cashew in each can. All right, so these measurements refers to percentage weight of cashews in each can. Is it okay? All right, so this is our X. So this is our X. So where's our X there? Our X is actually what? Percentage weight of cashew in each can. Is it okay? All right. So maybe we go and write this down. So X is percentage weight of cashew in a can. All right. And then we have this 23.5, this 3.1, right? This is the mean, this is the standard deviation. Now, this one, are they the sample data or is it from a population? Yeah, class. The 23.5 and the 3.1, are they sample data or population data?
They are samples.
Yeah, they are actually sample data. All right. So this one is actually our X bar. This is our small X bar. This is our small s. So this is the small s. All right. And this is our small X bar. Okay. All right. Yeah. So that's why you see it here. Yeah, over here you can see also. Yeah, you see I write this down, right? Okay, now can y'all see that this one is sample data? They are not population data, right? Why is that so? Because it follows, you know, when you read the problem, it's like reading a storybook, right? See, reading storybook, so you see they mention here, inspector takes a random sample of 31 cans and measure the percentage rate of cashew in each can, right? And then immediately follow this, they say the mean and standard deviation of these measurements. These measurements, meaning what? Meaning from the 31 cans. Is okay? All right, so that's why these are the sample data. Okay, So now we've done until here. Do these results constitute strong evidence in support of the inspector's belief? Okay, now this sentence is very important. Do these results constitute strong evidence in support of the inspector's belief? All right, so looks like it's a yes or no answer, right? And how do we know yes or no? How do we know whether these are sample results, whether they support the inspector's belief or not? How do you know? Well, that means you need to go and test. All right, yeah, you need to go and test. Test what? Test, any idea? What do you want to test? You want to test what? You want to test the inspector's belief. Is it okay? All right, so they ask you whether the sample results support the inspector's belief or not, right? Yeah, so that means whether the inspector's belief can it be true or not, right? Yeah, so you need to go and test the inspector's belief. Yeah, everybody okay or not? So this will be our H1. So our H1 is going to be the inspector's belief. All right. Okay, so now we know what is our H1 already. Yeah, H1 is the inspector's belief. Okay, can you all tell me what is the inspector's belief? So now we must go and search, right? So actually, what is the inspector's belief? Anyone?
Less than 25%.
Can you repeat?
Some less than 25%.
Oh, okay. Yeah, you say something about what less than 25% are cashew, is it?
Yeah.
Okay. How do you get to this one?
I mean, the earlier statement is saying that the cashew is kind of overstated. So yeah, I think the inspector should believe that the cashew should be less than 25%. Yeah,
that's right. So actually, it's because of this word here. All right. So you see, the question says, the label says that 25% are cashew, right? And then they say, suspecting that this might be an overstatement. Then an inspector takes a random sample of 31 cans and he go and measure this kind of thing, right? So this overstatement is actually the inspector's belief. Overstatement. All right, so he thinks that the label is an overstatement. So overstatement means what? The label says 25%, right? Overstatement means what? He believes that more than 25%, less than 25%. Overstatement means what? He believes that there are, well, more or less.
Less.
Yeah, it's less. All right, less than 25%. All right, so I think I hope everyone is now clear that the inspector believes that there are less than 25% of cashew in the can. All right, less than 25%. Okay, now the thing is, how do we write this down? All right, how do we write this down? Okay, going back to our summary. So summary. Okay, going back to here. Now you realize that we only test two things. It's either the population mean or the population variance. All right, and you're looking that this is our X. Everybody see your right hand side here? This is our big X here. Our X in this question is percentage weight of cashews in a can. All right, now you want to test the inspector's belief. Inspector thinks that there are less than 25% of cashew in the can, right? Yeah. So to test his belief, should we go and look at the mean percentage weight, or should we go and look at the sigma square? That means variance of percentage weight. He believes that there are less than 25% of cashew in the can, right? Yeah. So to write this down, to write down his belief, how to write? Is it related to the mean percentage weight of cashew in a can? Or do you think it's related to variance of percentage weight of cashew in the can?
It's gonna be the mean.
Yeah, it's mean. All right. It's mean. I hope it's quite intuitive to you all that to express the inspector's belief, we should look at the mean percentage weight of cashew in the can. All right. So it's the mean. So then we go and look here. So inspector's belief is what? Let me write here. Yeah, I hope we can write here. So inspector's belief is H1. All right, H1. I use a blue color, right? Yeah. Okay, so H1 is what? Mu. That means the mean percentage rate of cashew in a can. He believes that it's less than 25%, right? So that means mu less than 25. It's okay. All right. So this is the inspector's belief. This is the H1. All right. And what we all know from the video that I always write down the H1, right? And then I go back to write down our H0. All right. So maybe we should put the H0 in front rather than behind. So the H0 here, then of course will also be on mu. And we'll always put equal sign. Then equal to what? Can it be equal to any other different number? Cannot. It must be the same number. Okay. Right. So this is our H0 and H1. Is that all right? Yeah, class, everyone okay or not? Any questions? Wait, looks like no question. Good. Anyone want to ask me why I put 25? Why I don't put percent? Should I put a percent here or not? Yeah, class, do you think we should put percent? Maybe here, should we also put a percent? A percent or no percent, there's a difference. Should we put percent?
Why no
Shouldn't
percent
it
above?
be 0.25?
You want to
Wait.
put 0.25?
Wait.
No. Of course, if you put percent, that means actually it's 0.25. If we don't put percent, then it's just 25. So now the question is, your X is percentage weight of cashews in a can. All right. So should we put a percent here?
No.
Yeah, actually no need. Yeah, because they already say it's percentage weight. So you no need to put percent again. All right. So it's actually just 25. All right. Okay. So I hope it's okay. So you can see that we are actually testing mu, right? So if we go to our table to see testing mu, right? Our case is which case? Is a sigma known or not? So we see what is given. Do we see sigma here? There's no sigma here, right? Yeah, so that means it's a sigma unknown. So this case is sigma unknown. All right, so we'll need X bar to be normal, prerequisite, and we are going to use T, test statistic T. All right. Okay, class, how to make X bar normal? We need to write down the prerequisite here first. How to make X bar normal?
The theorem.
What?
Theorem.
Theorem. Oh, what theorem?
The CRT.
Okay, central limit theorem. Yeah,
That's the one.
You see here the sample size is greater or equal to 30, right? Yeah. So we can use central limit theorem. All right, so here's what we say. By central limit theorem, X bar is approximately normal. All right, so this satisfies the prerequisite already. All right, and now we can go through all these 4 steps here. All right. Okay, so we go through the 4 steps. So the first step is we'll write down the H0 and the H1. Okay, so this is just now we already discussed this. And from this H1 here, you see less than, right? So lower tail test. So later on, we know what the rejection region is like. Oh, yeah. Okay, so here. Okay, so now the second step, we go to the test statistic. So test statistic here is the t. Okay, so this is the t. This mu naught here, this mu naught, this number here, actually is the 25 here. All right, yeah. So the mu naught is 25. Then the s the n all this you know, right? Yeah. So we just go and put in the numbers. Then what we are getting is called the value of the test statistic. So we put in all the numbers. Okay, so we get this thing here, right? Then the next thing is we are going to step 3 lah. So we are going to draw rejection region. Okay, draw rejection region. Now ours is what kind of test? So now ours is what kind of test? Lower tail, right? Hey, lower tail. So that means something like that, right? Something like this. So what kind? Well, how should we draw it? How should we draw? So we know that it's like this, right? Can you tell me what curve are we drawing?
T
Yeah.
curve?
What the probability distribution? What probability distribution are we going to draw?
SMT dispersion.
It is the t distribution. All right, we should be drawing the t distribution. You follow the test statistic. Okay, so you see the test statistic is t. So that means we will be drawing the t distribution. All right, t distribution is also a bell curve. So we have a 0 in the middle. And then I'm going to type here. So this is a t with n-1 degrees of freedom. n-1 is 30, right? So 30 degrees of freedom. Okay, right. And then we know that it's going to be a lower tail test. So lower tail means like that. Okay, and this is the rejection region. And we know that the area is alpha. Yeah, so this is the alpha here. Okay, now in our question, the alpha is what? 0.01, right? So the alpha here is 0.01. But this number here, we cannot find directly. Okay, so if I show you the table, then you'll know why we cannot find directly. Let's go to the t table. Here. Now this one is our t table, right? So everybody is looking at this t table, right? So what is tabulated here? See all these numbers here, they are actually the t subscript alpha, right? So you can see that they are all on this side. But this one is on the other side, right? So it's on the other side. So it's not here. Okay. However, because of the symmetry, what you can do here is that if you go and draw something here, right? You go and draw something here, having the same area. That means this area also the alpha, also the 0.01. And then this number you can find. All right, now this number here is just t subscript alpha. Yeah, so this number you can find. Okay, so it's actually t subscript 0.01 which you can find. And then to get this number, this is your critical value, is just negative of this. Can you all see? All right, so that's by symmetry. So this will be just minus t alpha. Yeah, so that's by symmetry. So this one you can find from the table and straight away you will know this. All right, so if we go and look at these, our degrees of freedom is 30, right? Yeah, 30. And you can see 30 is here. Now this is our table, right? As you can see, degrees of freedom 30. And then your alpha here is 0.01, right? Oh, it's not here. It's actually on the next page. All right. There, you see 0.01 is here, right? Then you can see 30, 0.01, and you are going to get this number here. Okay, 0.01. All right, so this is your T alpha. And of course, our critical value is what? Our critical value is going to be minus T subscript 0.01. So it's like that. So it is our critical value. Right, so you see, this is our critical value here. Then we see the value of test statistic minus 2.69. Okay, class. So here we need to be careful when you put down the minus 2.69. So actually it's on this side. Okay. All right. So if it is on this side, so it actually falls. Like this is called inside or outside of rejection region. Anyone? Hey, class.
Inside.
It's inside the region.
Yeah, it's actually inside. All right. So it is inside of, that means what? Reject H0. Okay, reject H0, accept H1. Yeah, reject H0, accept H1. So if we see here, oh, want to reject H0, we want to accept H1, right? So of course we'll write this down. And then just now we also know that H1 is what? Is the inspector's belief. All right, so you want to accept the inspector's belief. Okay, yeah. So now we can go and draw conclusion now. Okay, so we need to answer to the question, right? So first of all, we say test statistic falls inside rejection region. So we reject H0, accept H1 at 1% level. And then we say, now we want to answer to the question, no? So we say at 1% level, there's a strong evidence in support of the inspector's belief. All right, well, we can also write down the inspector's belief. So this completes the question. Any problem? Okay, no problem, right? So let's do the next one. Okay, let's do the next one. Okay, so once again, let's go and read the question. Identify the big X. Right, so we have the manager of a production facility claimed that he did not meet the production orders last month because the variance. Now, everybody can see this word variance, right? Because the variance of what? Maybe it's variance of X, right? Variance in production times, okay, of different workers was too great. So now it gives us an idea already. What is our big X there? Big X is production time of a worker. Is it okay? All right, that gives us that kind of idea. X is production time of a worker. Okay, so yeah, so that's what we think. Let's go and, okay, I'll write down later. So he thinks that well, he did not meet the production order last month because the variance in production times of different workers was too great, resulting in too many delays, right? So he said the standard deviation was over 30 minutes for the workers in his plant. Well, here, unfortunately, they didn't say standard deviation of what. All right, so here didn't give us anything, but he said standard deviation was over 30 minutes. Okay, so you must decide if he's right. So you sample the production times of 25 workers from his plant, and you find that S is this. Okay, let's analyze this. So you want to see whether he's correct or not, right? So you sample, what do you sample? Sample the production times of 25 workers from his plant. Okay, class, what is this 25? This 25 is what? What is this 25?
Sample size.
Sample size.
Sample size.
Yeah, sample size. All right, so this one is actually sample size. Okay. So this 25 workers, what did he sample? He sampled the height, the weight. No, he sampled the production times. All right. So meaning that your sample data are actually production times. All right, sample data are production times. then you know that your sample actually should be the same as the big X, right? So if your sample data are production times, so that means your big X is also production time. Yeah, make sense? Okay. And as for this, S equal to 23, wow, this one very clear lah. So they're telling us that the sample standard deviation is 23. Okay, so maybe I go and write this down first. So it's quite confirmed already. Your X is production time of the worker at the plant. Okay, yeah, so this is what we have. Okay, now we come to the very important sentence here that tells us what is our H1. What do you think of his claim? Okay, what do you think of his claim? What do you think of his claim? How do I know what to think? How do I know what to think? Unless I go and test his claim. Yeah, make sense? So how do you know what to think? Well, you don't know what. So what you can do is go and test his claim. Test the manager's claim. Is it okay? All right, so you want to test the manager's claim, right? That means that your H1 is the manager's claim. Okay, so H1 is the manager's claim. So what is the manager's claim? Anyone? This is your X. Your X is production time of a worker at the plant. Then what is the manager's claim?
He did not meet the production orders last month.
Yeah, I know he did not meet. But
over
that's not
50
really
minutes for work. Is it the standard deviation?
He did not meet the production order last month. That's not his claim. That one is a fact. But what?
Less than equals to 30. No.
What is it?
Less than equals to 30.
Yes. Yeah, you see this sentence, right? This is the manager. This he is the manager. So he said the standard deviation was over 30 minutes for the workers in his plant. All right, so this is actually the manager's claim. And I think from this claim is also very clear, right? We say standard deviation of production time, okay, was over 30 minutes. So that means, you go and type here. So why like that? Yeah. Something wrong here. Let me clean up this dot here. Let me see whether I'm able to type. Okay. So he thinks that sigma is more than 30 in his plant. Is it okay? All right, so that's what he thinks. Okay, so H1 is sigma more than 30. And of course, then you all know the H naught. H naught is actually, of course, must also be sigma, cannot be a different thing. And then here, we just always put equal. So equal what? Of course, cannot be equal to anything else. Must be the same number. Okay, so this is your H naught. This is your H1. Everybody okay here? All right, all? Okay, then we go to our summary to see. Why like that? I think I clicked the wrong thing. What happened? I think I clicked something really wrong. Okay, so let's see here. So actually here, we notice that we only test mu and sigma square, right? Yeah, we only test mu and sigma square. And we notice that this one is sigma square. It's not sigma. All right. So coming back to here. Yeah, coming back to here. We see here that what we have is only sigma, right? So how do we change the situation there? So very simple. You just put a square here. Then here also square. That means everything we go and square. Then becomes sigma square, right? So that will be the same as our summary. It's okay. All right. So it's a testing of sigma square. Okay, y'all. And then let's see whether the file is still here. Okay, so it's here. All right, so what is the prerequisite? Let me see. Oh, test sigma square. We need x to be normal, and we are going to use the chi-square test statistic. Okay, right. So what is x normal? Well, x is production time of worker at the plant, right? Is x normal? Wow, out of the whole question here, can you all see the word normal?
No.
Not fine, right? It's not mentioned. So it's not mentioned, then how do you make sure x is normal?
Is it the central limit theorem?
No. The answer is no. Our central limit theorem is not on our central limit theorem. Go on, my central limit theorem is not here.
Do you assume it?
Limit theorem is here. Now everybody go and take a look at central limit theorem. Everyone can see central limit theorem. N greater or equal to 30 implies what's this? X bar. X bar is approximately normal. That's central limit theorem. Okay, so central limit theorem has got to do with X bar. It has nothing to do with X. So what do you do here? How do you get X?
Assume. Just assume.
Yes. Yeah, just go and assume. Yeah, so don't use central limit theorem. Even though our n here is 25, well, even if I change the number to 35, also cannot use central limit theorem. Is it okay? Because central limit theorem is for X bar. So the only thing you can do here is just to assume X is normal. All right? It's very easy. Yeah, another thing, a very common mistake here is that people go and write assume X is normal, but they don't define the X. So that's not correct. Okay, you need to define the X, and then you say assume X is normal. Otherwise, people don't know what is your X, right? Okay, yeah. Okay, so now we got this already. And what do we do now? Oh, now we go and go through the 4 steps. So first step, go and write down your H0 and your H1. Is it okay? Where's my tutorial? Then here. Sigma square more than 30 square, right? That's our H1. Okay. So because this one is more than, so we know it's going to be an upper tail test, right? So that's the first thing. Then the second thing is we are going to do the test statistic, right? The test statistic in this case is the chi-square. Okay, so it's the chi-square. Okay, yeah. Now this sigma naught square. This sigma naught square here, this one here, right? Sigma naught square actually is what number? Actually is 30 square. Is it okay? This number here, sigma square more than what? This constant here. This is what we call sigma naught square. All right? Yeah. Then just go and put in the values, and that will give us the value of test statistic. Notice that here, before we substitute in the value, we call this chi-square, right? Then after we put in the value, we change the notation a bit. Here we put in a hat here, yeah, just to indicate that this is the value. Okay, then we get this number, right? So now we'll come to the third step, and the third step will be we'll draw the rejection region. All right, so notice that this is upper tail, so we know what upper tail is, right? Okay, I'm going to draw. Let me draw here. The thing here got space for me to draw. Yeah, I think so, So I'm going to draw here. Now, what should we draw? Actually, in statistics, we only draw 3 kinds of graphs, right? Only 3 kinds. The Z, standard normal, T, and chi-square. We only know how to draw these 3. All right, so what should we draw here?
Chi-square?
Yes, draw chi-square. How do we know draw chi-square? you follow the test statistic. Test statistic here, chi-square, right? So we'll go and draw chi-square. So chi-square is like a wave. So everybody has been to the wave, right? For exam, right? Oh, okay, so this is a chi-square. So let me type here chi-square. Actually, I should draw the chi-square here. Let me type. So chi-square with n minus 1 degrees of freedom, which is 24. Yeah, so this is chi-square with 24 degrees of freedom. All right. So I'm going to put in the rejection region, which I know is a upper tail test. So upper tail means this tail. Yeah, this is a tail. All right, see the one that I'm shading. This is called upper tail. And what is the area of the rejection region there? It's always alpha. All right, for one tail test, it's always alpha. In our case, our alpha is 0.05, right? So that means this is 0.05. So this is going to be called chi-square. And we know that it's always subscript alpha. All right, subscript this area. So in our case, it will be chi-square subscript 0.05, right? Then we just go to the chi-square table. Chi-square table. This one is chi-square table. Chi-square table here, right? Our degrees of freedom 24. This one 24 here. You can see 24 here, right? Yep. This is my ruler. Okay. Our alpha is 0.05. You see here alpha 0.05, right? I can see that it's going to be this number here. Everybody can see? Yeah, alpha is 0.05. So this is the number. All right, so 36.42. Okay, let's go to the next page to see. Yeah, let's go to the next page to see. So yeah, you really get this number here, 36.42. Okay, so these are rejection region. And this number 18.4 is actually our just now, the value, right? Yeah, the value is 14.1. Why I put 18.4? Because it is a typo. Okay, so this one should actually be a 14.1, right? Right, so this is the number 14.1. Is it all right now? Yeah. Anyway, this 14.1 is here. So is this inside or outside of rejection region? Yeah, class?
Outside.
It's called outside. Okay. Yeah, outside. Everyone agree? Yeah, outside. So it is outside. That means you have to accept H0 because you cannot reject. So okay, you accept H0, you reject H1. Okay, reject H1. Now, noting that H1 is the inspector's belief. All right, so you are going to say, you accept H0, reject H1. And then because H1 is actually the inspector's belief, right? So what do you think of, sorry, not the inspector's belief, it's the manager's claim. So what do you think of his claim? So we conclude that his claim is not substantiated. Right, so you conclude that the manager's claim is not substantiated. Everybody okay? All right, yeah. So there's this question here. Okay. Any questions?
Prof, for the would it be marked down if we wrote central limit theorem on the top for the X thing?
No, you cannot use central limit theorem for X.
Okay.
You can't.
Would we
because you see there, your central limit theorem.
Would we be penalized for writing that if we did it in the exam? Okay.
If you write the wrong thing, then of course you'll be penalized, right?
Yeah. Okay. Thank you, Prof.
Okay. Yeah.
Prof, can I ask, when calculating the chi-square, right? When you key in the value, you must write the hex on top of the X. Is that like crucial when we do for exam or what?
Are you talking about what the one stripe? Do you mean do you mean
Yeah, the small thing above the X.
mean
Is that
this
like
one?
crucial?
You mean this chi-square hat, is it?
Yes, ma'am.
Chi-square hat, you are asking me if you don't put hat whether important or not, is it?
Yep.
Then you go and put a hat, right? Well, since I put the hat, then you also go and put the hat on. Is it okay?
Yes.
Okay.
What's the meaning of the hat again?
Oh, the hat here. Actually, nothing. Just to indicate that it is the value of the test statistic. Just like, previously we have a big Z, right? Yeah, it's my pencil. Previously we have sometimes we have a Z test statistic, right? And then when you come to the value, then you put a small Z, right? And then we also have a T test statistic. And when you come to the value, just now I forgot to say, then you write a smaller t, big T, then a small t, big Z, then a small z. Then we come to a chi-square, then we put a chi-square hat. Okay, all right now.
So the whole point is just to separate the test statistic from the actual value we're doing.
Make it a little bit different, no?
Okay.
Yeah. Okay, y'all. Okay, so I think that's all. Now let's go to something else. All right. If I go to the next question, now we complete statistics already, and we are going to numerical methods. Yeah. So let me go to numerical methods. So numerical method, I'm going tonight. We are going to solve equations. Okay, just solve equation. Yeah, problem is very simple. We want to solve equation, and the first method that we learn is called fixed point iteration method. So this is the first method that we are going to talk about tonight. All right. Okay, so first of all, you want to solve equation, right? You must know what is our problem. So our problem is actually like that. We want to solve this equation, fx equal to 0. Okay, of course, our fx may be very complicated, so that's why we don't know how to solve. That's why we use numerical method to solve. Okay, right. So let's go through this fixed point iteration method. This page is actually from our summary. Okay, you can see the file here, EE2006NM summary all. All right, yeah, so this is actually in our summary. It's also in our lecture notes. Yeah, so it's nothing new. So let's go through the 5 steps of doing this method. Okay, it's very systematic also. You can see there are 5 steps here. All right, so the first step, first step, now you want to solve this equation fx equal to 0, right? So what you do is you go and find an interval, I call it J, AB, that contains a root of this equation. Okay, go and find an interval that contains a root of the equation. So let me elaborate on this. How do you find an interval that contains a root of the equation? Yeah, I believe it's behind. So let me go to this page. I want to page down. Why cannot page down? Page down. Okay, page down. All right, so you want to solve this one, right? Okay, so the first step is you want to get this interval that contains a root x star. Okay, so this is just an explanation. All right, so you know that when we were in secondary school that time, last time we solve equation, you go and draw a diagram, right? So we say solve graphically. So you go and draw y equal to fx. Now, suppose this is your graph, okay? Then your graph cut the x-axis at x star. You can see the x star here, right? So that's the place where it cuts the x-axis. And what is the y coordinate at x star? Well, you know that because it's lying on the x-axis. So your y coordinate, which is fx star, is actually 0. The y coordinate here is 0. All right, so you can see fx star is 0, right? So that makes x star a root of this equation, fx equal to 0. All right, because fx star gives you 0. All right, so x star is actually a solution. Yeah, okay. All right, then what we do here is that you want to get interval that contains this root, right? So maybe we can go and draw a diagram. Now, of course, from the graph, it's very easy to see. Then you can say, oh, this one is A. Then I just call this point B. So you can see that the interval AB contains x star, right? That's very clear from the diagram. Okay, let's look at the attributes of A and B. I see this one A, right? Let me put a dotted line here until it touch the graph. Okay, yeah, so this part, this distance here from here to here, this is actually what? This distance is actually called FA. Yeah, agree? I mean, this is like the y coordinate, right? Until here, this is actually the distance FA. Yeah. So likewise, from here, point B, if I go and put a line up, then it touch the curve, right? So the distance from here to this point, wow, that is also the y coordinate, right? So this is actually FB, FB. Yeah, FB. Yeah, everybody okay or not? So this is the distance FB, this is the distance FA. All right, okay, yeah. And then what we can see is that, I mean, it's quite clear from the diagram. Your FA is positive or negative,
Negative.
Yeah, because it's below the x-axis, right? So FA is negative. Your FB, what kind of thief? Positive, negative, what thief?
Positive.
Yeah, FB is positive, right? So you can see that FB is positive, but this FA is negative, right? Yeah, this FA is actually negative. Negative. All right, so you can see that, oh, one positive, one negative. So that's actually the characteristic of the interval AB. All right, so what is the characteristic of this interval AB? The characteristic is that FA, FB, one of them positive, one of them negative. Yeah, so that's why, because one of them positive, one of them negative, that's why your x star is in the middle, because your function, your f is continuous. All right, so here negative, here positive, so it has to cross the x-axis. It must cross the x-axis. And when it crosses the x-axis, you get the root of the equation. All right, so it's like that. So that's why we have this conclusion here. Okay, you see FA negative, FB positive, right? When you multiply together, one negative, one positive, meaning that the product is negative, right? Product is negative. So therefore, your x star is in AB. Is it okay? Is it all right? Yeah, so that actually tells us how to get this interval AB. So what we do is that you just go and get some number A, get some number B. Well, it's actually trial and error. Then you calculate FA, calculate FB. If one positive, one negative, that means the product is negative. That means there's an x star in the interval AB. Is that all right? Okay. All right, so that explains step number 1. Okay, so this explains step number 1. So I already tell you how to get this AB, right? By trial and error. But usually, in the question, most of the time they give you the AB. Yeah, they give you the AB, you no need to go and find. But even though they give you the AB, but you still need to show that there's a root inside. Okay, how do you show? And you just go and get FA times FB to see whether negative or not. All right, if negative means there's a root inside the interval AB. All right, so this is the first step. Now we go to second step. Okay, second step is your original equation is fx equal to 0. Okay, you go and rewrite Go and rewrite and you shift the terms here and there. Okay, go and rewrite and you make it into the form of x equal to a function of x. Okay, just do this. Now, of course, different people, they have different ways to get this x equal to gx. So this x equal to gx, different people will get different gx. Yeah, because you do differently. So that's why this function gx also can turn out differently. All right, so it's not unique. So then the third thing is you want to go and start your this fixed point iteration. Okay, you want to go and do your fixed point iteration. So let me go to another page to explain to you. I want to page down. Okay. Oh yeah, it's here, right? So I say here rewrite this one to this one, right? So that means fx equal to 0, you manipulate, and then this is equivalent to x equal to gx. Okay, and then what you do here is you go and set up your fixed point iteration method. And this is the fixed point iteration method. What you do here is your x here, you put x subscript n plus 1. And then this x, you go and put xn. So xn plus 1 equal to gxn. And your n is from 0, 1, 2, 3, and so on. All right. Now, this is called fixed point iteration method. All right. It's an iteration method. So how do you do this method? Very easy. You put n as 0 inside. That means here x1, right? Then this one is x0, right? This will give you x1. The x0 actually you go and provide. Your x0 is you provide one. Okay, so that's why this is known. Then you put inside your function g, then you calculate. That's how you get your x1. Okay, then you follow this again. This time you put n as 1. When n is 1, then this one becomes x2, right? So your x2 is gx1. Now you already got your x1, right? So you put inside here. That's how you get your x2. So likewise, you go and do until when? Well, you're hoping that it will converge. Your x1, x2, it will converge to one number. Hopefully, it will converge to this root called x star. So if this one converge to x star, then your x0, x1, and so on, it will also converge to x star, right? That means you will get your equation like this. And the moment you get this, meaning what? Meaning that your x star solve this equation, x equal to gx. And then because your x equal to gx is equivalent to fx equal to 0. Equivalent, right? So meaning what? Meaning that your fx star is 0. Right? So that means this one, if it converges, it will converge to the root of fx equal to 0. Right? So then you will get your solution. Okay, yeah, and of course here everything we write like this is based on the hope. So the hope here is that you want your xn to converge to x star. All right, okay now. So now this one is only a hope, so it may not realize. It may not realize. So that's why you need to do some testing. All right, you need to do some kind of testing. Now to do this testing, let's go to this page here. There's a theory inside our lecture notes. And you see here, convergence of fixed point iteration. All right. So you see here x star is the solution. G is continuously differentiable in some interval j containing x star. Then if you have such an inequality, g prime x less than equal to a constant L, and your constant L is less than 1 inside your interval j, then our iteration process, which is this fixed point iteration, converges for any x naught in j. All right, now I know this is quite long, so let's summarize. Now j is an interval containing this root, right? So if we have this condition, g prime x less than or equal to L, and L must be less than 1 for all the x in J. Then what? Then your fixed point iteration process converges for any x not in J. All right, so this is the summary, and this will be our step 3. So our step 3 actually is to test this. Do we have this condition? If we have this condition, that means our fixed point iteration will converge. Okay. Yeah. So it all depends on this condition. Okay. And then of course here, I guess I think everyone will have this doubt here. You know, this L here. Actually, what is this L? What is this constant L? How do we get this L? Because you must get this L. Because otherwise, how do you know whether less than 1 or not, right? Unless you go and find the L. And this L is actually the maximum of g prime x, maximized over x in J. That's the meaning of this. You see, g prime x absolute less than or equal to L. So meaning what? Meaning that your L is like the maximum, right? Maximized over all the x in J. So this is our L. So in fact, we need to go and find the L and then go and see, is this less than 1 or not? Okay. Yeah, so it's all this inequality. Need to test this. So if you have this, that will guarantee convergence. And this is actually our what? It's actually our fixed point iteration method. This is the third point. So if I show you the third point now, see, check g prime x less than or equal to L less than 1 for all x in J. Is this true? If true, then you know that the fixed point iteration process will converge. If not true, then means what? Does it mean it will diverge? May not be. Okay, just that you cannot guarantee. So anyway, we go and check this. So if this one fails, then you just go back to step 2. You go and write in a different way, go and get a different G, then go and try step 3 again. All right, so keep on trying until this one is passed. Yeah, suppose pass already, pass already, then what? Then you go and start this one. Then now you can start the iteration. Okay, and you will start it with x naught in J. So it's up to you to choose what x naught you like, as long as it is inside J. All right, then this one, your xn will converge. Okay. So it's like this. Yeah. Then after this, what do we do? Okay, I see we do, you know, if you have no stopping criterion, you will be like doing forever, right? So you need a stopping criterion. Okay, so I need a stopping criterion. Let me go and look for a stopping criterion. Okay, let's look at page 3 here. 3. Wait, now stopping criterion. Also got the theory behind one. Okay, so first of all, inside our lecture notes, we got this theorem. It's called error estimate. So what it says is that your x tilde, and you know the curly thing on top is called tilde. So this x tilde is approximate root, and this x star is a root of equation 1. Equation 1 is actually fx equal to 0. So both are inside AB. Now suppose your f is continuously differentiable on AB, and this is the important thing. Your f prime x is greater or equal to m, which is more than 0 for all x in AB. So suppose you have this. All right. Then means what? What is the conclusion? So the conclusion is this. Your approximate root, your x tilde minus x star is your exact root. Okay, the absolute value. So this is actually like absolute error. Okay, absolute error, which is equal to this. This is an absolute error, less than or equal to fx tilde. You see, you put your approximate root inside and take absolute value and divide by m. All right, so how big is the absolute error? The absolute error is less than or equal to this quantity. All right, you see, absolute error less than or equal to this quantity. So that's why this is called error estimate. It tells you how big is the absolute error. Absolute error is what? Less than or equal to this quantity. Right? Yeah. So that's it. That's the one. Okay, here about the M here. Now this M, actually, what is this M there? The M here, you know, when you say f prime x greater or equal to M, right? For all the x here, right? So your M is like what? Like the minimum of f prime absolute, and you minimize over all the x in AB, right? So that's why we say our M here is minimum of f prime x absolute. Okay, all right. So in our problem, we need to find the small m, right? And that's how we find the small m. Okay, right. Now here, it's still not yet enough to get the criterion, the stopping criterion. There's some more theory behind, and it's on the next page. Now on the next page is also something from our lecture notes. What it says is that a number that's correct to n decimal places has an absolute error, this is an absolute error here, less than 0.5 times 10 to the power minus n. Right, so this is also absolute error equal to this thing, less than 0.5 times 10 to the power minus n. Okay, if your number is correct to n decimal places. Okay, right. So now you have this one here, and you also have this one here, right? So now we are going to combine them. Here, absolute error less than or equal to this, right? Then this one there is for a number that's correct to n decimal places, right? So the absolute error between this number and the exact number should be less than 0.5 times 10 to the power minus n. So now let's combine them, right? Combine them into the next page. So you combine this one and also this absolute error less than this. Hey, from our theorem, absolute error less than or equal to this, right? So now this is your approximate root. Now your approximate root is this, right? Suppose, well, this one is actually imposed by the question now. So usually they will say, I want your approximate root to be correct to, you know, certain number of decimal places, right? So in this case, how do you make sure? So what we do here is that, now this part is our theorem, absolute error less than or equal to fx tilde divided by m, right? And then you just set. Now here I put less than, right? But this less than is we impose one, we set. Okay, you set it to be less than 0.5 times 10 to the power minus n. Because if you do so, then you will have absolute error less than 0.5 times 10 to the power minus n, right? Which will mean that your this x tilde is correct to n decimal places. All right, so that's why you put it here. All right, yeah, you put it here. And now your this thing here, it actually gives us the stopping criteria. All right, so you just go and test this. You can calculate this quantity. You want this to be so, right? So you go and see, is it really like that? All right, so this is the stopping criteria, right? So that's the stopping criteria. If this one is fulfilled, well, meaning that your x tilde is really correct to n decimal places, and then you can just stop. If this one is not fulfilled, that means not yet. All right, so you too soon, cannot stop yet. So still carry on your iteration and go and try again. All right, so you see, this is a stopping criteria. So that's the theory behind this. All right, so now if we go to our, just now our method now. Hey, I see here, this step number 5 here is actually the stopping criteria. This is our stopping criteria. All right. And here I give it a specific, suppose I want to correct to 3 decimal places. All right, 3 decimal places. So what we check is our iterate, the xn is your fx tilde absolute divided by m. Is it less than 0.5 times 10 to the power minus 3? The 3 here is because we want 3 decimal places accuracy. Right? So is it less than? So actually this one is a question mark. You need to go and see. Right? It's a question mark. If really like that, that means your xn is correct to 3 decimal places. If this one no, no, then how? That means not yet, not yet. So carry on doing and go and try again. Yeah. Okay. So these are the 5 steps of our fixed point iteration method. Okay, now. No, so you can see that actually every step behind got theory 1. Okay. Yeah. So these are only just the summary of the steps. Yeah. Okay. So now so in practice we'll do 1, 2, 3. And in practice, we want to calculate the stopping criteria first. So in practice, your step 5 actually you put here. Yeah, after you go and check pass already, then you go and get your stopping criterion before you start. Is it okay? All right, yeah. Okay, let's go to our question now, and we'll see how we go through all these steps. Right now, so I think then you will be clearer. Okay, use the method of fixed point iteration. To solve these equations. Give your answers correct to 3 decimal places. Right, so that's why you see here, this stopping criteria is really 10 to the power minus 3. Okay. All right. Go through the steps given in the lecture notes. That means you go and do the step 1, 2, 3, 4, 5. Right. Now, this is the first question. Okay, so this is your equation. Then you notice that here they put x is in this interval, right? So they actually give you the interval AB here. This is your interval AB. Yeah, this is the interval AB. All right, so there will be a root inside. Okay. So even though they give you AB, but you still need to go and show that there's a root inside. Is it okay? And you notice that they also give us the hint. And the hint. In the hint, they actually give us the gx. Yeah, so they also don't want us to anyhow go and get any g, which may not converge. All right, so they actually give us the g here. Okay, so let's go and do this question. Okay, before we do the question, let's recall that our problem is actually fx equal to 0. This is our equation, the equation that we are going to solve. And that is, our steps are actually based on solving this equation, right? So here, well, straight away you can tell this equation that they want us to solve, it is not this form. And y'all see, it's not this form, right? So the first step that we are going to do is to make it into that form. Yeah, so you see, this is the equation given, all right? And it's not in that form, so we need to rewrite it. Okay, so you rewrite into the form fx equal to 0 so that you know what is your function fx. All right? So what we can do is you shift everything to one side. See that I shift these 2 terms to the left-hand side. Then I get your fx here. So now I really get fx, which is this function, equal to 0. All right, so this is my fx. Okay, any questions still here? Okay, so looks like okay, y'all. Anyone want to ask, should we shift to the left or shift to the right? Well, class, anyone? You want to ask whether we should shift to the left or shift to the right, or doesn't matter?
Doesn't matter.
Yeah, actually it doesn't matter. Okay, later on it will adjust. Okay, so it doesn't matter. Okay, so now we are ready to do the steps. Okay, let me go to our steps. Okay, first step, here they say find interval j that contains a root, right? So we know actually this is our interval j, but we must still go and show, right? So remember how to show? Maybe I put a note here. So this one here actually is the FA less than 0. Okay, FA times FB less than 0. So, so this is what we will do. Okay, so you just go and find FA, go and find FB. Well, you see one positive, one negative, right? Okay, so that means the product is negative. So this shows that there's at least one root in this interval j. So this is our interval j. All right. Then step 2, rewrite into the form x equal to gx. All right. Well, they actually give us the gx, right? So we just go and figure out how they get this g. All right. So this is how they do it. We write to this, right? So originally, this is their equation. From this equation, they get x equal to gx, right? X equal to gx, and this is their gx, and this is their gx, right? Can y'all see how they get this g? Class, can y'all figure out or not from this equation how they get to this g? You know what they do? Any questions?
Divide the power throughout.
Yeah, yes. We take the fifth root. That means power 1/5. Okay, so you take power 1/5 left hand side and right hand side. So that's how you get to here. All right, so this is our gx. Now we go to the third step. Okay, we want to see whether this gx is going to give us convergence or not, right? So you see, we want to check this. Now, actually, when we say check this, the main thing is to find the L. Only when you find the L, then you will know whether less than 1 or not, right? You can't do this if you don't know L, right? So we must go and find the L. And how to find the L? Then you see it's below. L is maximize G prime X absolute over J, right? Let's see it's here. Okay, we have the GX, right? So let's go and maximize the G prime. All right, maximize. So to determine a convergence scheme, right? So that's our step number 3. So I'm going to calculate the L, maximum of G prime X, X over J. All right. Well, you got your G, so the first thing we do is go and differentiate. Go and differentiate and must put absolute value. Okay, so this one is differentiate absolute value. Wow. If your X is inside this interval, then certainly whatever inside is positive. Okay, so you can just throw the absolute value away. So that gives you this. Okay, all right. And if you write nicely, then it's like that. Because you notice this one is negative power. See, negative power means 1 over the power here is 4 over 5. Yeah, this one you all know or not? Negative power means like that. Is this okay? All right, So now what do we want? We want to maximize, right? Okay, maximize this thing over J. J is here. Maximize over J, this thing. How you maximize over J? So what value of X you want to substitute inside so that you get this one maximum? What do you think?
One.
1. Yeah, you're right. You're right. If you put in 1. So actually, we call this kind of function a decreasing function of X. All right, decreasing function of X, meaning that as X increases, decreasing function of X meaning like this. Maybe I draw, then you'll be clearer. This is decreasing function in X. All right, that means as your X increases, the value of the function there actually decreases. All right, so this is called decreasing function. All right, so if you want to get maximum, right, suppose this is your x-axis, you want to get maximum. So where should you put your x in there? Obviously, you want to put your x here, right? And put your x here, right, where you get the maximum, right? Okay, and this is the smallest x here. All right, and the smallest x here is 1. Okay, yeah. The smallest x here is 1. So that's why you see here, the maximum is we substitute x equal to 1. And that gives us this value. Is it okay? All right, so you see we get the L already. Yeah. All right. Okay, so you can see very well that our L is below 1, right? L definitely is less than 1, right? So you have found already your L is below 1. So that's why you can say your G prime X less than or equal to L, and your this L is below 1 for all the X in J, right? So therefore, our fixed point iteration xn plus 1 equal to gxn, right? So you know your gx, okay, put the x as xn. So this is your formula. Later you use this to do your calculation. So this one converge for any x not in J. All right, okay. Until here, is it okay? All right.
Sorry, ma'am. Can you go back to page 9? Okay. Thank you. That's all.
All right. All right. So then after this, we are ready to go to what? The stopping criteria, right? Before you start, let's go and get the stopping criteria first. Okay, stopping criteria here mostly is to calculate the small m. I need to calculate a small m, right? Which is minimum of f prime absolute over j. So I'm going to do the step 4 to get stopping criterion. I'm going to calculate this, right? So first of all, I need to find f prime x. Now, earlier on, we already got the function fx, right? Okay, let's go and differentiate. Differentiate, then you get this thing, right? Then you know I'm going to absolute value. But this thing there, actually absolute value also the same, because this thing is positive. It's very clear, all right? For x inside this interval, your 5x power 4 minus 1, it is positive. All right, so absolute value is also this thing. Okay, and what we are going to do? We are going to minimize. All right, so this one is also absolute value. Yeah, you want to minimize. So what do you do here? And minimize, right? And you look at your function, 5x power 4 minus 1. Now, this kind of function is as x increases, your function value will increase. It's like that, okay? As your x increases, your x is here. This is your x. As your x increases, then you know from this expression that your function value will also increase. Okay, so this kind is called increasing function. So for this kind of function, if you want minimum, right? Okay, let's go and get minimum. Minimum. So minimum of this, right? So minimum means what? You want to put in what x to make it minimum? Now, increasing function. You want minimum, right? So you should put in your smallest x here. Because your smallest x here will give you the minimum function value, right? Yeah. And the minimum x here is 1. So you will put in your x as 1. Okay, so this is your small m. Any question here? I hope it's intuitive. Okay, so I get the small m already. So that means f prime x greater or equal to this m, right? For x in this j. And I can now put in the stopping criteria. So stopping criteria, this is our absolute value, less than or equal to this. Okay, and this one is I put in my small m. My small m is 4. Okay. And this one is you set one. Okay. The front part is actually the theorem 1.1. So you wait until here. And this one you set it to be less than 0.5 times 10 to the power minus 3. Because you want to you want your xn to correct to 3 decimal places. All right. So this one you need to go and test. Every xn you must go and test this. Yeah. So we got stopping criteria already, all. So now we can actually go and tabulate. Yeah. So let's go and tabulate here. So first of all, I can I'll pick x naught inside j to start our iteration. So I pick x naught as 1. Okay. 1 to 1.5, you can pick any number. All right, just pick something simple. So I see that 1 looks like a simple number, so I just pick 1. So there's no other reason. All right, just that it looks simple. Okay. All right, so these are the things that I need to tabulate. Obviously, your n, your xn. Okay, xn is actually where you put down your answer. And this one, I also need to tabulate this because you need to check. Yeah, because you see, you need to check what? Now you need to check this quantity. Is it less than 0.5 times 10 to the power minus 3? Okay. Yep. So let's go and start. So when n is 0, you pick your x naught to be 1, right? So n is 0 means this is x0. So this is 1. Now here I didn't bother to check. So I guess maybe not so soon. Then I go and get my x1. This is my x1. Then this one I really go and calculate. Then I get my x2. No, I can see still not yet. Must be less than 0.5 times 10 to the power minus 3, right? So still not yet. Then this one, oh, this one reached already. You can see that this one is reached already, right? So should we take x3? Should we take our answer to be x3 then? Theoretically, you can take x3, theoretically, because that's what our theory says, right? If this one less than 0.5 times 10 to the power minus 3, oh, that means this one is correct to 3 decimal places. However, in practice, then we feel that maybe this one not safe enough. Because you know, when you calculate your xn, inside also got error, you know, all kinds of error, round off error, you know. And then when you calculate your fxn, then also got error, right? Yeah. So even your 0.186 times 10 to the power minus 3 here is also not accurate. Yeah, it's not accurate. So, well, is it really less than 0.5 or is it very close to 0.5? So you feel that maybe not so safe. So then you just want to be safer, then you go and do another one. You know, you try to do until this is like you know, one level up. This is 10 to the power minus 3, right? So now it's 10 to the power minus 4. Well, obviously now 10 to the power minus 4, right? Is it less than 0.5 times 10 to the power minus 3? Yeah, of course, right? And it's much further apart, right? Yeah. Okay. So therefore, we'll pick this one here. So we'll pick x4 as our number. Okay. So therefore, we say here that we'll take x4. 3 decimal places, right? 1.028. That's correct to 3 decimal places. Is it okay? Everybody okay here? Any questions? Okay, no question, is it? All right, if no question, then let's come to the number of decimal places to write down. Actually, the number of decimal places to write down, then the xn, we should write down 8 decimal places. Okay, because if you write down too few, well, noting that you're using this xn to calculate the next xn, right? So if you write down too few, then you will affect the accuracy. Okay, so all the xn values, we should write 8 decimal places. Okay. And then of course you want to ask me, you say write 8 decimal places, why you only write 6? Well, actually I want to write 8, but then there's not enough space. So that's why I cannot write 8. Okay, not? But you all got plenty of space, right? Yeah. So you can write 8 decimal places here. All right, any questions?
Hello, Prof.
Yeah.
Can you hear? Yeah. Prof, I want to ask, right? You say take x4, right? Can we also take x3 since it's also below 0.5?
Yes, you can, theoretically.
So both are accepted for x3 and x4.
Yes.
Okay.
X3 is theoretical. Theoretically, you can do that. X4 is practically you want to be on the safer side. So then you do further.
Oh, okay.
Yeah.
All right. Yeah. Thanks, Prof.
One is theoretical, one is practical. Okay.
Okay. Good.
Okay, let's do the last part here. Okay, so the last part here, I'll go faster because the steps are the same, just that we change the equation. And see now equation change. Interval also change. And the gx they give us also different. All right. But the steps are the same. All right. So let's go through the steps. Okay, you got the interval j, right? So you need to show that there's a root inside. This interval j, you got to show that there's a root inside. Before you do that, you notice that our equation is not in the form fx equal to 0. Right. So what do? Go and rewrite. Yeah, rewrite into this form. So you put everything to one side. So now you got your fx. Okay. Okay, step 1. You want to show that there's a root inside AB, right? Okay, go and calculate FA, FB, FA, FB, C1 negative, 1 positive, right? Okay, so that means fx equal to 0 has at least one root inside. Okay. Okay, step 2, rewrite. Well, actually, they give us the gx, right? So we just need to figure out how they do it. Okay, rewrite to this form. This is the original one. And now they give you this gx, right? Can you see how they do it? From here, how it becomes like that? What do you think they do?
Divide EX throughout, then square root the answer.
Yeah, that's right. So I wonder whether the rest, so it's actually divide by e to the power x, right? So it's like this. Okay. So this one, when you have 1 over e to the power x, it's actually e to the power of minus x. Okay. All right. Then after that, square root. So when you square root, then your x becomes x. Your x squared becomes x. Then this one square root of, it becomes power minus x over 2. Okay. So that's how you get to here. Right. And then now we do a step number 3, right? Yep. Let's do step number 3 now. Okay, to determine this convergence scheme. So basically, you want to find the L. Let's go and find the L. So we are going to calculate this one. Okay, we have the gx, right? Let's go and differentiate. Differentiate the g to get the g prime. This is g prime and must take absolute value. So we differentiate, you got a negative sign here. So throw that away. So this one is positive. Yeah, you can see it's e to the power minus x over 2, right? And because of the negative power, the negative power, so this makes this a decreasing function of x. Is it okay to you all? Because this is actually 1 over, 1 over e to the power of x over 2. Yeah, this negative power thing means 1 over. All right. So you can see that when your x increases, this value actually decreases. So it's a decreasing function, right? Okay, so if this one is a decreasing function, then you want to maximize, right? And you want to maximize. So what x can we put in there to make this, maximum? Your x is inside 0.5 to 1. So what x you want to put in to make it maximum?
1.
Yes,
1.
1. If you put 1 inside, it's decreasing. It's decreasing function. Decreasing.
Oh.
So if you want maximum, you should put the x in front, right?
0.5.
Yeah, yes. Yeah, so you need to put the 0.5 inside. See, put the 0.5 inside. Well, another way to look at it is that you put the 0.5 here, then your denominator is small, right? So 1 over a small value, that's how you can get a big value. So that's how you get this L here. Put your x as 0.5, right? And obviously our L is less than 1. So that makes us very happy because pass already, right? So we are sure that this scheme will converge for any x naught in J. So this is our step 3 lah. So let's go and do step 4 now. And step 5, go and get this stopping criteria. Go and get the small m. Now small m different, it's a minimum of f prime. Just now it's g prime, right? Now it's f prime, and it's a minimum. Okay, so let's go and get this. Okay, our function f, just now we have it. Let's go and differentiate. Okay, differentiate, we get something like that. Well, it's positive. So absolute is also this one. We want to minimize. So what do you think? You look at your function here. Do you think it's increasing or decreasing with x? You all know e to power x, right? You know what it looks like, right? E to power x is like this.
Increasing.
That one, right?
Increasing.
Then 2x also increasing. Your x squared also increasing. So combine is also increasing, right? Everything is increasing. So it's increasing. Then you want minimum. So you want minimum. What value of x should we put in? You want minimum, You want minimum, right? You want here, right? So what value of x should you put in here?
0.5.
Yes, put in 0.5. All right, so minimum, put in your 0.5. Then you get this number. So this is your small m. Okay, now you've got your small m already. And that gives you the stopping criteria. All right, so your absolute value less than or equal to this. This is your small m. And once again, you want to check. All right, although you put less than, actually you're not sure one. Okay, so every time you need to check, is it less than 0.5 times 10 to the power minus 3? Okay, let's go and tabulate. Okay, I need to pick an x naught, right? So here I go and pick 1. Our interval is 0.5 to 1. I pick 1. Wow, the only reason I pick 1 is because it's a simple number, right? So I got my n, my xn. This is my stopping criteria, the one that I need to check. Okay, so I pick 1. Okay, here I didn't bother to check. I go to the next one, then I check. Not yet. Not yet. 4 also not yet. But you can see the value is getting smaller, right? Yeah. So then we do this one. Still not yet. Maybe the next one can already. It's the next one, right? 0.348 times 10 to the power minus 3 less than 0.5 times 10 to the power minus 3. Theoretically, you can stop here. Theoretically, you can stop here. You can take your x7. All right, but we are really not say very comfortable because you see, it's both are 10 to the power minus 3. And this number is also not say very far away from 0.5, right? So we feel not so comfortable. Then do some more. Do some more. Well, better. Now 0.123, right? Well, smaller, but still it's 10 to the power minus 3. Well, then you know we want to be very safe one, right? So then you do one more, then you get to here, wow, 10 to the power minus 4. Wow, this time you really feel very safe. So if you want to be safe, then we just take x9. All right, and x9, 3 decimal places. Of course, you see the next number is 4, right? So you just truncate. So you just take 0.703. Right? Is it okay, class? All right, now any questions?
Professor.
Yeah.
So actually, we can just take the x7, right?
Yes, that's right. So this is a theoretical.
All right.
Theoretical. This one is called practical. It's also called Yasu. Okay. All right, now class.
All right.
Okay, any more questions?
Professor.
Yeah.
Yeah. So I know that there's another method, the Newton-Raphson method. So how do we know which one to use?
For this question, they specify us to use this method.
No. I mean, let's say it's not specified. Like, how do you know which to use?
Actually, I would use a Newton-Raphson method.
Always.
Because that one is simpler to use. Number one, simpler to use. Next week we'll do that one, and you know that it's not 5 steps. In fact, I think it should be below.
3 steps.
Yeah, only 3 steps. So it's easier.
So
number one is easier. Then number 2 is it converges faster than a fixed point iteration method.
So for every problem out there, can I just choose to use Newton method instead of the fixed point?
You can do that unless the question specifies.
All right.
Yeah.
Okay. Thank you.
Okay. Hey, any more questions? Okay, no more questions, right? Oh, sorry. Tonight a bit long. So let's stop it here. So I meet you next week. Okay, bye-bye.
Bye.
Thank
Hey,
you.
bye-bye.
Bye, Prof. Thank you.
Bye-bye.